So these represent your 4 stages.
Yes.
Okay, so let me get a different group because I'm gonna have to ask them to answer a few questions. So you guys are so good there.
It's not when it touches.
Hogsmeade, you're gonna answer some questions for us. Ready? Hogsmeade, what do you think is the appropriate principle when we go from here to here?
Conservation of energy.
Conservation of energy. What do you think is appropriate principle from here to here?
Conservation of momentum.
And what do you think is an appropriate principle from here to here?
Also conservation of energy.
How many of you guys would agree with those 3? That it's conservation of energy, conservation of momentum, conservation of energy. All right. I would agree with that. So here's what you must do now. This is what the change is. This is what we're adding today. Because this one is very similar to one we did yesterday. So here's what you're adding. I want you to tell me what controls each stage. You can use an equation if you want. You can use words if you want. But something is changing and something is staying the same. How do we affect the change? So I'll give you an example. In the first one, you said it's conservation of energy. So what is staying the same between these 2 stages? Energy. That's the right answer. Energy stays the same between these 2 stages. Does momentum stay the same during these 2 stages? So that's something that's changing. Momentum is changing. Can you explain why? Maybe or maybe not. We're just trying to figure out what stays the same and what changes. So come up with the things that stay the same and the things that change during that transition. Again, if you want to use an equation, great, do so. If you want to use words, fine. But we're going to pick another table, and they're going to go through all 3 of them.
The first one, the second one be if momentum is conserved and momentum is conserved and energy changes and step 2, there's a new force. There's an extra cell. What do you have flipped? Step 2 is the conservation. You have the 4 that you have.
This one's time, that's time at this. So I have just like,
Oh, you lined up one. Oh, I see.
So I guess that's T1. Yes.
The final one would be energy and momentum.
No, it'd be the same as energy.
Yeah, I think I would say
Couple minutes more.
Constant equals the kinetic energy of M1.
Yeah, okay, so something like that?
Yeah.
All right. So you tell me the following things. What stayed the same between these 2 stages?
The momentum. No. The energy. The momentum.
So not the momentum. Now, because you guessed wrong, and generally I don't see you as a guessing type, how do you know the momentum didn't stay the same?
I don't know, but I think conservation of energy, then you know momentum changes. It just
I'm not trying to put you on the spot, David.
The velocity changes?
The velocity change, yeah. It started from rest and then it has some velocity. So did the block have any momentum before the spring was released? No. Did the block have momentum after the spring was released?
Yes.
Yes, so the momentum changed. It's that simple. So was there a collision that caused that momentum to change? No. So obviously something external caused the block's momentum to change. So when you're making these, we're writing out these statements, you guys tend to use the wrong vocabulary, either because you don't understand the vocabulary or because you don't know which word you should use. But if you state or if you believe that the energy is conserved, it's staying the same. Stick to the principle. One of the statements in these graded lessons is that you have an internally consistent argument. Internally consistent would be thwarted if you were to say energy is conserved so the momentum stayed the same. That's not internally consistent. Do you follow me? So if you want to earn that 1 point that almost all of you universally give yourself, you have to be internally consistent. Now, here are the things I want you to be able to express here. What thing about the block did change? I think there's a couple things you could say. The velocity changed, and what else? We just talked about it. Yeah? The energy didn't change, it stayed the same. But what thing about the block did change? The momentum changed. Right? The energy in the system stayed the same because the energy is the spring block system. But the momentum of the block changed and the speed changed. Now, here's the next thing. We're trying to figure out what stayed the same and what changed. Right? In this stage, if you wanted to make the block go faster, what could you do? I could increase the spring constant. What's something else we could do? We could decrease the mass of the block. What's something else we could do? Go ahead. Increase the distance we pull the spring back. Now, in your notes, look at what I'm doing, okay, and what I'm asking you to do. I'm asking you to do 3 things. The first thing is, what is the principle? Do you guys know what the word exemplified means? Being made an example of. Exemplified. So this is an example of conservation of energy. So then what stays the same and what changes? This is our version of pre-writing. You don't have to do all of this, but this is what I need you to think about when you're getting ready to write one of these essays. And this is the most important. This is where you guys fall down the most. What controls that change? So in this one, we know that energy is being conserved. So the energy before the spring is released equals the energy after the spring is released. What's staying the same? The energy is staying the same. What's not staying the same? Well, momentum's not staying the same. The block's acquiring momentum. It's also acquiring a velocity. What controls that? The spring constant controls it, the amount that we pull the spring back controls it, and the mass of the block controls it. Do you see what I want you to be able to do? So if you can do this for each stage, you can write to these problems better. So we have 2 more transitions, 2 more stages, and we've already got kind of a guiding discussion about what is controlling them. So let's see if we can't answer the other 2 questions. So take a minute, think about the other 2 questions for the transition from here to here and from here to here. And I'll pick 2 different groups to kind of help us with that.
Said what stays the same is the conservation of momentum, and because momentum was conserved, the kinetic energy was lost because right before the collision, right after the collision, the act of the collision caused the change of velocity, and that was what changed in step 2. Cause and effect.
Okay. So can you sum that up one more time for me?
Okay, so so right after when the collision happens, that causes the velocity to change, which means kinetic energy is lost after the collision, but momentum is conserved.
Okay, there's many things there I think that are good. So, yes, all the things she said. The only thing I would add to that is use the word inelastic when you can. When you know the energy's changed, we know the boxes are sticking together, say it's an inelastic collision. That strengthens your argument that you understand that the energy changed. So another group even asked about that a minute ago. I think that's great. So the last thing about this then, about that transition, about that step, is remember, part of what I want you to do is ask yourself what controls this change. Now, there's probably 3 different things you can say to talk about what controls this change. Would anybody like to offer one of them? Go ahead.
Mass changes?
So, when we discuss the masses, is it clear to you that whatever the ratio of these masses are, that's going to determine what the final velocity is? That if m1 is small compared to m2, we're probably going to lose a lot of the velocity because m2 is in the denominator. If m1 is big compared to m2, then we probably won't lose as much because the big block will just overpower the other one. You understand what I'm trying to talk about here? So the first one is the ratio of the masses probably determines the result of the collision. You need to be able to express that somehow. Yeah.
How is it in the denominator?
If we're looking at what the final velocity is after the collision, then we would take this and solve for final velocity. That's solving for final velocity. It puts m2 in the denominator. Now it puts m1 in both the numerator and the denominator. So you guys, I'm not sure if you know this or can put this in your head easily. Grab your calculator for just a second. Ready? When they're the same, how much does the velocity change? When block 1 and block 2 are the same mass, how much does the velocity change? By half, right? 1 in the numerator, 1 plus 1 in the denominator. So it's a half. If block 1 is twice as big as block 2, two-thirds. So is it clear that the final velocity is higher if block 1 is bigger than block 2? Okay. What if block 2 is bigger than block 1? Let's say block 2 is twice as big as block 1. You see that that's less than if they're the same. I mean, that's the kind of math we're talking about here. It doesn't have to be hard. We want you to be able to have a rational idea of what's happening. Now, there is another possibility, one that's not in this problem, but one was on your test. What if they don't stick together? What if the collision isn't a perfectly inelastic collision? In fact, what if block 1 bounces off of block 2? Right? That would affect the final velocity as well. That's not what's happening here, but what we asked was what things would affect the outcome. You need to be prepared for an argument that includes these different things that can affect the outcome. All right, one more transition. Then we're going to shift gears. So I'll just pick this one to make it quicker. I've already done that one. Hoth, you're on the hot seat. Tell us about the last transition. Now, I'm not saying that we're trying to find a way to give you talking points, something that you can write in your interview. Interview. I'm glad it's not an interview. Something that you can write in your essay. When you're writing that essay, you need to be able to address all of the things that affect the outcome of your problem, but they are going to focus you. Remember in your test, they asked specific questions about what was conserved and what wasn't. You guys remember that? They pulled the one block against a spring and they asked you, was momentum conserved between T0 and T1? And a lot of you lost points in there because you mixed up momentum and energy, and once you started writing and you were under duress because it was a test. But I want you to frame the problem. but look at the things that are connected. It is clearly true. Changing d affects this energy, affects this velocity, and therefore affects that height. All things being equal, d would make a change in the height of the system. You may have to express all of it all the way through. Now, this is one where I'd say we have what's called a linear set of events. One thing happens, then another thing happens, then another thing happens. What if instead we had something where there are two possibilities for what could happen? Right? This is the pumpkin question. They gave you three possibilities of what could happen. And in those possibilities, you had to determine which would make the object do something more. So here's our two examples. I have a dart being fired at a block. In one example, the dart bounces back and the block lands on the floor. In another example, the dart sticks to the block and both the dart and the block land on the floor. Now, can you envision this question? Like a question in which they're going to ask you which one is greater, R bounce versus R stick? Because I can envision that being a question. So what I'd like you to do is to first see if there's any stage being left out. I think there is. And from there, let's see if we can find ways of talking to the problem. We don't have very much time because we're on special schedule. So hit the high points so that we stay in this moment. But what I want is what stays the same, what's different, and what seems to control the transition from one stage to the next. I'm sorry, but there's only 3 minutes, so we're gonna have to bring this to a close. I think you have to focus on the idea that either this happens or this happens. This is the immediate outcome. The first thing that happens is a collision. So from here to here is conservation of momentum. Two different kinds of collisions, but conservation of momentum. Now, yeah, we should focus on how these are different, how what's happening here is different in each case. We have a perfectly inelastic collision, and then we have one where the thing bounces off. You have to figure out in which case there's a different velocity. Obviously, something must happen here that's different. But after that, what is our next principle that we have to work with? What's governed in going from here to here or here to here? Does it look familiar? We're a little more concerned here. There's a change in height. Could you use conservation of energy? There's probably things about it, but we're interested in the range. What principle did we talk about that had range in it? Projectiles. This is a projectile problem. Again, identify what the principle is or what the property is. There are things about projectiles you should remember. For example, what's the same in both cases? The height of the table, which means what? Same amount of time to reach the ground. That's important. That's something that you would need to say. What is the same? The height. And why is that important? It determines the time. You can't just say the time. You have to indicate because the height is the same, the time is the same. But here's the kicker. This is the thing. Projectile motion is about range. You have to bring to bear the things that contribute to the range. And there are two. There's the horizontal velocity and the time. So these are the things that control a projectile. Remember, it's about what's the same and what's different. So you've indicated the time is the same. You need to figure out now how to deal with talking about the velocity. first period is having trouble with understanding why bouncing off imparts more momentum than sticking to. Are you guys having trouble with that? Because if so, we're going to see the difference tomorrow. We'll try and help us with that.